Okay, so hello everyone. Once again, I welcome you all. In which in this session, so we are discussing about uh, the subject which is the fundamentals of manufacturing processes. And from the lecture 7, we started the basics of the metal cutting. Okay, so 7 and the 8, that is last lecture in which we discuss about the basic terminology. Okay, and yeah, we have discussed about the basic terminology. So today we are going to discuss this the third session on this for this unit. So today we are going to define some of the relationship. Okay, these relationships are very important. Okay, because on the basis of these relationship only, whatever the angles that is given to us, accordingly we are measuring the thickness, length, and the velocities as well. Okay, so, and then we will discuss about the relationship between the different velocities. So, three velocities we have seen in the last time in the basic terminology, that is cutting velocity, tip velocity, and the shear velocity. So, that we will define the relationship between them. Okay. So, first, we are going to define the relationship between the chip thickness ratio. Okay. That is, we are defining by the small r. Okay. Rake angle, that is defined by the alpha. Okay, and the shear angle, that is defined by the phi. So first I'm just drawing a figure, then we will discuss it. Okay, so this is a common figure. Sorry. Okay, and here there's a normal to the surface. Okay, now this is just assume that this is a single point cutting tool. Okay, okay, and in this direction the chip is coming out. Okay, so these things we have seen in the last time. Okay, so this is the workpiece. This is the workpiece. This is tool. Okay, and this is the chip. Now we are going to define the relationship between R, phi, and alpha. So if we talk about individually, that what is alpha is this. Okay, this is alpha. What is phi? Phi from the horizontal. This is the shear plane. Okay, that's why we are defining it as a shear angle. So from the horizontal, this angle is basically the phi. Okay. Now, if we talk about the R, that is chip thickness ratio. So this R is defined by the T by TC. Okay, so what is T? T is basically the uncut chip thickness, and TC is what? That is a chip thickness. Okay, so if we'll see the uncut chip thickness, then this is the length, the depth of cut that we are assuming in the beginning. That is, we are defining that is uncut chip thickness. Okay, and from here, from the from this point, over to the tool rake face, we are just drawing a perpendicular. Okay, so this is 90-degree. So this is the TC. Fine. Now what I'm doing is I'm just drawing a perpendicular from here. Okay, over this horizontal, and I'm defining these by the names like A, B, and this is C. Okay, so here, okay, first is we are just looking the into the triangle. This point defined by the D. Okay, this is which is a perpendicular meeting at the tool face. Okay, rake face we can say. So first of all, here we are defining. We are using this. We are taking this triangle which is A, B, and the C. Okay, so this one. A to B, B to C, and C to A. Okay, so this is A, B, C. We are taking this triangle. So this is 90-degree. Okay, so if I draw this triangle, then right, so this is A, this is B, and this is C. Fine. So like if I define here the relationship, that is AC. What is AC? We have already seen that. By the way, if you want to define, then we can. Otherwise, AC is also manageable. Okay. So by the way, we have seen that this is a shear primary shear thickness. Okay. So this is TS. Okay. and this A to B. So this A to B is basically the perpendicular to the horizontal, and if you will see, then this is equal to the uncut chip thickness, that is T. So and this angle is phi. So can we find out the relationship between T and TS by using the phi? Okay, so this is a 90-degree means a 90-degree angle triangle. So using this is just, I'm just taking this sine phi. Okay, sine and cos we are defining. So when you will see, this is the angle, this is perpendicular, this is perpendicular, this is base, and this is hypotenuse. Okay, so here the perpendicular and the hypotenuse is given to us, so we can define, we can use the sine. So sine phi equals to, that is sine phi equals to uh, perpendicular to the hypotenuse. Okay, so here the perpendicular is T and the hypotenuse is TS. Fine. So here from here I am taking the value of TS, and that would be equals to, that will be equals to T by sine phi. Okay, so this is equation number 1. Fine. Now here, if you will see, let's see the triangle which is ADC. Why? Because this is a 90-degree. Okay, because this is normal to the rake face. So this is the angle. Okay, this is the 90-degree. Now I want to find out this angle. Okay, this angle. This angle I want to find out, because this is exactly we don't know. So we can find out this angle. Okay. So if you will see here, just I'm making this one. So this is the perpendicular. Okay, this is horizontal, and this is the rake face. Fine. Now here in this direction, this is basically the shear, primary shear or shear zone, we can say. So this angle is phi, this angle is phi, and this angle from the perpendicular to the rake face, this angle is alpha. So if this is the perpendicular to the horizontal, then we can say that if this is phi, then this is how much? This is 90 minus phi. This is 90 minus phi. So now this angle will be equals to 90 minus phi plus alpha. Okay, so I'm just writing this one like 90 minus phi plus alpha, so I'm taking this one. Okay, so this is 90 minus phi minus alpha, in bracket I'm taking. Okay, so this is the angle. Now this angle is measured. So now if you will see, if I want to make this triangle, then this triangle would be like, okay, this is A, this is D, and this is C. Okay, so this is 90-degree, and this angle is how much? That is 90 minus phi minus alpha. Fine. Now this is, if you will see this one, AC. Now AC is what? That is TS. Okay, that is shear thickness. Okay, and this AD is basically the perpendicular to the rake face, so this is equals to TC. Now here the same thing which we applied over here. So this is the angle, and this is perpendicular, and this is hypotenuse. So again the same thing, that is sine 90 minus phi minus alpha, that will be equals to perpendicular upon hypotenuse. So perpendicular is what? That is TC, and hypotenuse is TS. Now if you will see this one, that is sine 90 minus something like that, means theta, for an example. So 90 minus theta, that would be in first quadrant only. Okay, but it will change from sine to, it will become cos. Okay, so cos phi minus alpha, right? From here we can get the value of TS, what we got in the equation number 1. So from here this TS will be equals to TC upon cos phi minus alpha. So this is equation number 2. Okay, so now we have used this figure. Now if you will see the equation number 1, then this is also defining the value of TS, which is a shear thickness. And if you will see the equation number 2, this is also defining the value of TS. So both the equations are same, means defining the value of TS. Then can we equate both the equations? Yes. Okay, so when you will equate both the equations, this will be like T upon sine phi equals to TC upon cos phi minus alpha, right? So what I'm doing is, I'm just taking this cos value, cos phi minus alpha, to this side, and I'm bringing this T over this side. Okay, so this equation will become cos phi minus alpha upon sine phi equals to TC by T. Okay, now what I'm doing is, this is cos phi minus alpha, so just I'm opening that one, that is cos A minus B. Okay, so I'm just taking that into next figure. Yeah, so this is cos phi minus alpha upon sine phi equals to Tc by T. Okay, so when you will open this cos A minus B, so it will be cos A, that is cos phi into cos alpha. When there will be a minus, then it will come to the plus. Okay, sine plus sine phi into sine alpha. Okay, upon sine phi. Okay, now this is Tc by T. Can I write this R equals to T by Tc? So this Tc by Tc by T, what will happen? That will be equals to 1 by R. So I'm writing over here that is 1 by R. Now I'm just dividing this sine phi individually to these two terms. So this will become like cot phi into cos of alpha plus sine phi will be cancelled out. So this will become sine alpha. That would be equals to 1 by r. So just multiply this r in this side direction. So in this side, so it will become, can I write this cot phi will be equals to 1 by tan phi. Okay. So this is r into cos of alpha upon tan phi. Okay. Plus r into sine alpha equals to 1. Now I'm just taking this term, that is r sine alpha, to this side, so it will become minus. So from this equation, that is r cos of alpha upon tan phi equals to 1 minus r sine alpha. Okay, so sorry, from here you can take this tan phi to this side and just take this to this side. So from here you will get the value of tan phi, that is equals to r cos of alpha upon 1 minus r sine alpha. So this is the relationship, and this is very very important, because here if you will see, then this is the phi, which is the shear angle, this is r, which is the uncut chip thickness ratio, and this is alpha, that is the rake angle. Okay, so this relationship is very very important, right? Okay, so this is the relationship between these three. Now let's move. Let's see one of the problem that is asked in GATE examination. So during the orthogonal cutting of a mild steel with a rake angle of 10 degree, means the value of alpha is given to you, that would be equals to 10 degree. Okay, the chip thickness ratio was obtained as 0.40. So the value of sorry, R is given to you. So the value of R is given to you, that would be equals to 0.40. The shear angle in degree evaluated from this data is, sorry, this is not data, this is data is. Okay, so you may have to find out the value of phi. So we have this formula recently we have derived, that is R tan phi equals to R cos of alpha upon 1 minus R sine alpha. Fine. Now just put the value of all the values given to you, that is R is given and alpha is given. So just put the value, that is 0.40 into cos of alpha, that is 10 degree, upon 1 minus 0.40 into sine 10 degree. Fine. So just calculate these values. So I am also calculating. Let me see, where is my calculator? Okay, so when you will calculate this top, the numerator, then it will be like 0.3939. Okay, and when you will calculate this denominator, it would be like 0.40 into sine 10 degree. Okay, minus point. So this will be like, what I'm getting is, that is 0.9305. Okay, so when you will take this 0.39 by 39 plus 0.9305, so what I'm getting is, that is 0.4233. Okay, but this is the value of tan phi. So just take the tan inverse. So when you will take this inverse, it will be like, what I'm getting is, that is phi is equals to 22.94. Okay, 3 or 4 degree. Okay, so this is the value that we will get, the value of phi. Okay, so this is the relationship, and this is a simple numerical problems. Okay, let's move to the next one, that is the relationship between VC and Vs. Okay, so V is basically the the cutting velocity, VC is the chip velocity, and the Vs is basically the shear velocity. So again, I am drawing the figure first, that is the workpiece, and means it's a very common figure in the tool geometry. Okay, this is and this is the chip. Now when you will see all these velocities are affiliated with these one, like this is the tool, so we are moving this tool to the horizontal, so this is the in this direction we are moving, so this is the cutting velocity. The chip is moving in this direction, so this is basically the VC, which is a chip velocity. And because of the deformation, that is deformation is takes place in the shear zone, in this zone. Okay, so in this direction the force is applied, because of that the deformation is takes place. Okay, and this in this direction the velocity is given to you, that is a Vs, that is shear velocity. Now we have these angles, like this angle, when you will see this one, this angle is phi, that is the shear angle. This angle is basically the alpha. So let's because let's derive this one. This we are making one of the triangle here. So A is if you will see with respect to this point, then in over this point, the horizontal direction, this is the V, which is a chip cutting velocity. In this direction, this is the chip velocity, which is VC, and in this direction, this is the VS. Okay. So with respect to this point, I'm just A's vector V velocity is basically the vector quantity. So I'm just shifting these. This is I'm just treating like just to draw the figure. I'm just using like this. Okay, so this is the horizontal, which is the cutting velocity. This is V. Okay, in this direction, this is the cutting velocity. So this is the cutting velocity, which is VC. Okay, and sorry. This is VC, and in this direction, from this point to this direction, this is shear velocity. Okay, so this is Vs, that is shear velocity. Now when you will see the angle, when you will measure this angle from this perpendicular to the shear plane, means from horizontal to the shear plane, the angle is basically phi. Okay, now this is VC. VC is basically on the tool face, okay, rake face from the vertical. So this is vertical, this is normal to the workpiece. So when you will see this angle is basically alpha. So if this is alpha, then this is how much? This is 90 minus alpha. Fine, this is 90 minus alpha. Now we don't know this value, so just assume that this is x. So this is a triangle, so the total sum of triangle will be equals to 180 degree. So we can get the value of this x from there. Okay, so this is x plus 90 minus alpha plus phi equals to how much? That is 180 degree. Okay, so this will be like when you will take measure this angle, this is 90. 90 will, and alpha and phi will move in this direction, so this is 90, because 180 minus 90, that would be 90, minus phi plus alpha. So I'm writing this like 90 minus phi minus alpha. So this angle is how much? This is 90 minus phi minus alpha, right? Okay, now what we are doing is why we draw this triangle, because this triangle, this is a vector triangle, we can say, or velocity triangle, we can say. So when you will see this, this is the velocity, and this angle which is in front of that, this is the velocity, and this angle is front of that, and this velocity on which this angle is front of that. So we can apply the sine rule over here. Okay, so what we are doing is sine rule, we are applying the science rule. Okay, sine, it's not science, it's sine. Okay, so sine rule we are applying. So what is the meaning of that sine? That is this is the velocity, and this would be angle. So this V upon sine, this is 90 minus phi minus alpha, phi minus alpha. Okay, and this is the velocity, and this is the angle, so VC upon sine phi, and this is the velocity and this angle, so Vs upon sine 90 minus alpha. Fine, now we can just we will just little bit easier this one, so make this easier. So this is V, and this is sine 90 minus theta. So again it's in first quadrant, and sign will change. So this will be not sine, but it will become sine to cos. Okay, so this is V upon cos phi minus alpha equals to VC. This will be same, this is sine phi and this will be like Vs upon sine 90 minus alpha. So again it's in first quadrant and it will become cos. So this is cos alpha. So this is basically the relationship whenever in the problems like the wherever like V is given to you, alpha and phi is given to you, and we have to calculate the value of Vc or Vs. That time we can use these relationship, or whenever like we have to calculate, or any angle or any velocity we have to calculate. That time we can use this one. Okay, so this is a easy relationship. Okay, guys, let's move to the next one, which is the types of the chips. So this is the last topic for today. Okay, then we'll stop for this one, for this lecture. So this is the there are three types of the chips generally formed. Okay, so first is basically the continuous chips. Now, what is the chip is, I think it's clear to you guys now that whenever we are taking this, like this is the shaft and we have to remove the material. So we are just keeping the tool like that. We are giving some depth of cut and then we are giving a feed to the workpiece in this direction. Sorry, we are giving the feed to the tool in this direction. So when it is rotating, when it will rotate, then time only the material can be removed. Okay, so whatever the material that is coming out, that is in the form of chip. Okay, now why it is continuous and discontinuous, that we will discuss. Okay, means what types, in what type of the this material can be removed. Okay, so this is continuous chips, discontinuous chips, or the continuous chips with built up edges. Built up edges, we are simply writing is BUE. Okay, that is continuous chips with the built up edges. So what is the meaning of that? When we can get the continuous chips, when we can get the discontinuous, or when we get the continuous with built up edges. So if that depends on uh, first of all, I want to brief you about the material. That depends on two things basically. First is material, that what material we are taking, and the second is like what parameters we are using. Okay, so if you will see the figure, simply I first of all I just want to brief you this figure. So this is like continuous chips. So this is like this is the tool and this is workpiece and this is the chip is coming out. So this chip is coming out, that is continuous, means it's not breaking in between. Okay, whatever the material is, we are moving toward this side. So whatever the material that has been started removing from the workpiece surface, it will be continuously folding. Okay, and when you will see the chips at the end, this will be like circular, it's a kind of like when you will see from the outside, it looks like a bolt has been formed. Okay, and it will be like threaded kind of portion. Okay, so this is the continuous chips. This is when it will be formed. Like whenever we are talking about the material, if we are talking about the material, then the ductile material we are using. If we are machining the ductile material, okay, then these kind of chips is generally formed. Okay, why this for the ductile material? Because ductile material is basically the soft material. Okay, this is a soft material, so it has some toughness. So whatever the material that has been removed, it is unable to break. Okay, because it has a high fracture strength. Okay, so it is unable to break. So that's why it is means it is soft, and because of that only the continuous chips is formed. When this discontinuous chips will be formed, when we are using the brittle material which is very hard in nature, that is hard in nature, and it do not have the whatever the energy that is transferred to the tool to the workpiece. It, whatever the chip is coming out, it do not has the energy to, it does not has the energy to absorb that one. Okay, so is it is hard, so little amount of the chip is coming out from the workpiece surface and it will break. Okay, then again as we are moving this tool toward this side, so chip is coming and break, again it's coming and break, it's like that. Okay, so this is the discontinuous chips will be formed. Now when we are talking about the continuous chips with the built up edges, this built up edge is different thing, but this is continuous chips. So same material like ductile material, it is formed for the ductile materials. Okay, so this is on the basis of the materials, that for what material what kind of chips is formed. Okay, so like if you will see this one, then this is a continuous, like chip is coming out and there is no breakage throughout the workpiece. Or if it is if it will break in between, then it's like sufficient amount of the strength that is gained by this whatever the chip is coming out, and it cannot bear its own weight. So that's only because of that only it is deformed or removed or cut it out. Okay, so otherwise it's a continuous throughout the workpiece as we are moving. Okay, now when you will see the discontinuous chips, like as these chips is coming out, and once like just try to assume that this is the first chip which came out. Okay, then it is deformed from here and then it's fallen. Okay, then this is the second chip which is coming out. It's not like first, second, third like that, but uh, in the beginning when we started, this chip is came. Okay, so this is for the time being, this is there, and then its break fracture is there. Then this is another chip which is like as the material is coming out continuously on the workpiece, so this is a kind of second, and again after some time it's fallen. This is the third chip, and again it's like that some amount of the material is removed, like as it is tool is moving in this direction, so some amount of material will come over the workpiece surface, and then again it's fallen. So actually what I mentioned here, that this is the one, two, and three. So it's not exactly like that, but when this one is deformed from here, it is fallen to the workpiece, or means fallen on the uh, bottom side of the machine, we can say. Okay, bottom side of the tool, we can say. So this is the first one that is deformed. Now another chips, which is second one, which is formed over here. So this is again fallen after some time, and this is the third one which is formed, and again it is whatever the length is achieved, at is again it will deform. Okay, so like that, this will process is happen. So this is the discontinuous chips. Okay, so this is happen when there's a brittle material we are using. Now, what is the meaning of build-up edges? That build-up edges is chip is coming out in this direction, and as I said that this is formed during the ductile material only. Okay, so what happened that is this is the primary shear zone through which the material is deformed, and now it will become chip. Until it is not deformed, it is a part of the workpiece material only. But once it is deformed, now it become a chip, means scrap material, we can say. Okay, now it's a deformation zone. But when this chip is coming out, this this is the tool, and this chip is coming out, so it will be move over the workpiece, sorry, tool, over the tool surface. Okay, over the rake face, we can say. So as it is moving like this, okay, so it is, there is a rubbing between the rake face and the chip. Okay, there is a rubbing between like that. Okay, because it is flowing over the workpiece surface only, sorry, uh, rake face, tool face. So as it is flowing over the tool face, so it is, there will be a rubbing in this, over this surface, right? So as there is a rubbing, the temperature is rises, the temperature is rises. Okay, as the temperature is rises, we can say like heat is increasing. As the heat is increasing, this chip which is coming out from the deformation zone, because the chip is coming out which is from the deformation zone, it itself has a high temperature. That is not the, means high temperature, we can say like whenever you will touch the chip which is coming out immediately, which is removed from the workpiece, it is hot. Okay, so it is hot and it is maintaining some temperature. So when immediately as it is coming out and it is rubbing over the tool surface, then the temperature is increases again. Okay, as the temperature is increases, there is a possibility that as it is a softer material, so it will stick to the stick to the tool surface. Okay, so it is stick to the tool surface, stick to the tool surface. Okay, but as it is stick up to some certain height, up to some length only, like not at the beginning but at some length only, from the this tip, we can say. From this tip, there is after some length only start uh, stick to the work, stick to the tool surface, and is it will stick, it will try to weld over the tool face. Okay, it will try to weld over the tool face, and it form this such kind of edge over there. Okay, now what will happen, because of formation of this edge, whatever the chip is coming out, now this edge is providing a kind of resistance to the chip. Okay, because now just try to assume that here some kind of edge is formed. Now this chip is coming out, so obviously it will not move like this. Okay, what will happen, it will try to move like that. Okay, but what will happen is, this is a metal, it's not like a wind or something like that, which is a less strength. It has some strength. So what will happen sometimes is the thickness of this build up edge is formed after some times, because of the strength, it's because of the strength of this uh, workpiece, or the chip is coming out, it has the velocity as well. Okay, so because of that, this built up edge is deformed. Okay, is this is deformed, it move along with the chip. Okay, again when this is completed, this is removed, again there will be a formation of another build-up edges. Okay, because the temperature is already raised, and again there will be a formation of the build-up edges, and it will, like, again the chip is coming out, it will reach to some certain height, and then it is stick, this will move along with the chip in this direction. Okay, so this is a kind of like whatever this edge is forming, we call this as a built-up edge. We call this as a built-up edge. Okay, so this is the built up edge. So what we are doing is, sometimes if there is a continuous chips or continuous chips with the build up edges, then what we are doing is we are keeping the chip breaker over here. Chip breaker is nothing but it's a kind of some shape, some kind of geometry that will try to break the chip, whatever the chip is formed. Okay, so these type of the breakers we are applying over the tool face. We are just attaching with the tool face. So as the chip is become like this, so it will it will, because of the deformation, it will become like this. So after that, this will be detached from whatever the new chip that is formed. Okay, so because here also we are using, so after some certain height, as it is moving in this direction, so that we do not want the formation of the build-up edges. If the build-up edges is formed, then definitely is because of the sticking, the surface of the tool will not be will be damaged, and the tool life is decreases. So we are keeping we are keeping these things into minds while going for the machining operations. So now this is the thing which we have discussed on the basis of material. Okay, like ductile material we are using in these two cases when the uh, continuous and the continuous chips with the built-up edges is formed, and the brittle material is used because that is a harder material. So there is a formation of the discontinuous chips. Now there are some parameters is also there, that is a feed and the velocity and depth of cut. Okay, so that feed is we have discussed, that is feed is what, that is it is rotating and we are moving the tool in this direction. So this is basically the feed, that if I'm saying that 1 mm per revolution, it means that this is when it will rotate completely one rotation. Okay, that time this is moved in 1 mm. Okay, like that. So if I'm saying that is 1 mm per revolution, it means that this tool, this workpiece has completed one revolution and this tool is moved 1 mm. Okay, in this direction, like that. So if second is like velocity, so velocity, that is cutting velocity, as we are moving this tool in this direction, so with respect to what velocity we are moving. Okay, next is the depth of cut, that what depth of cut we are taking. Okay, yesterday basically I forget the terminology, basic terminology of the shaft. Okay, because I discussed the things, but I discussed this one only, but I forget to mention the terminology which is we are using in the machining of a shaft when we are mounting on a lathe machine. So I'm just using that one. Okay, and then I will discuss that parameter part. Okay, so this is the shaft that we have. Okay, and this is basically the diameter. This is basically the diameter, and this is final diameter that is we have to achieve. So just try to assume this is D dash. Okay, this is D dash. Fine. Now here we are keeping the tool. By the way, this tool we are keeping here only in the beginning. Okay, but after some times only we are looking for this picture. So this is the depth of cut. This is the single point cutting tool, and this is the depth of cut that is maintained. Okay. So and we are moving this tool in this direction. So this is the feed, that is mm per revolution. Okay, right. So for an example, like is we talk about any of the material. Okay, for an example, if we are increasing, for an example, like here just try to assume that we are keeping this depth of cut up to this only. So this is the depth of cut initially we are taking, just try to assume that is D1. Okay, and in the second case we are taking this depth of cut which is like this. So from here this is D2. So now D2 is greater than D1. Okay, this is the depth of cut, that is D2 is greater than D1. Okay, so if the depth of cut is increasing, then what will happen? We are keeping this feed and velocity and all the other parameters constant only, this rotational speed also constant. So what will happen in that case? The friction in between the workpiece and the tool will increases. So if the workpiece, if the friction is increases, it means whatever the chip that is formed, that will be larger length. Okay, so if larger in length, definitely it needed larger forces, but we are keeping other parameters constant. So what will happen? If you will increase the depth of cut, then the chances of discontinuous chips formation is increases. Is we are using the, if we are taking very small like 0.2 0.3 mm, we are reducing in a single stroke, then the formation of the continuous chips is there. Okay, so if the depth of cut is less, if the depth of cut is less, then there is a chances of continuous chips, the formation of continuous chips. Okay, if we are increasing this, then there is a discontinuous chips. Okay, discontinuous chips. One more thing is there, that there is a feed is there. Okay, feed is there. So if we are taking like whatever, for an example, now we are keeping this depth of cut constant, that is d we are taking. Okay, now f1 we are initially we are assuming that is 1 mm per revolution, 1 mm per revolution, and the second that is let's just take that is 5 mm per revolution. Okay, means when initially okay, just try to assume that this is 5 mm per revolution, this is 5 mm. Okay, that is achieved, and this is 1 mm. Okay, this is 1 mm. So in, while keeping this depth of cut, in the second first case we have reached from here to here only, from here to here, and in the second case we have reached up to here, means 5 mm in one revolution we have achieved. So what will happen? In, when we are increasing this feed, that time the formation of, because uh, when we are using this depth of cut feed, less feed, that time what will happen, that is there is a no, there is a there is a continuous formation of the chips, and this is also very small, this feed. So what will happen, the formation of continuous chips will be there. Okay, and if we are increasing the feed, means from here initially we came here, means initially it's here, and then in one revolution it is reached here, and like that. So if we are increasing this feed, then the formation of the discontinuous chips will be there. Okay, so if we are talking about the less feed, then there is a formation of the continuous chips. Okay, and if we are talking about the high feed, then the formation of the discontinuous chips will be there. Okay, in this terminology, like if we want to calculate that what is the final diameter, what will be the final diameter, and what is the initial depth of cut we are taking. So if you will see this one, then this is also the d. Okay, so this capital D will be equals to 2 times of the small d, that is depth of cut and final diameter. So from here you can get the value of d minus 2d. Okay, so this is the depth diameter, final diameter, in case if you want. Now here also, like in the formation of these chips, you can ask, we can add one more thing, that is the lubrication. Okay, on the basis of that also, like if we are taking the lubrication, then once if we are taking the lubrication in terms of water and the oil content we are taking generally, so what will happen because of that, whatever the temperature is rises, that will be like managed. Okay, again it will cool. So the what is the temperature is rises, because of that the formation of the buildup edges is formed, that will not rise. So what will happen, there is a very less chances to form the buildup edges. So whenever like we are going for a machining of a shaft from which we are removing the material, especially we are talking about the ductile material here. So what will happen, we are using this lubricant, and because of that we do not want that there will be a formation of the built-up edges. That will basically reduces the strength of the tool as well as life. Okay, so this is all about my from my side in this lecture. In the next lecture we will discuss about the geometry of a single point cutting tool. Okay, and also what is the tool signatures that we are using. Okay, so that we will discuss in the next lecture. Okay guys, so thank you so much.